Hi, everybody. This is Dr. Nigro with the Chem Calculations screencast. This screencast is going to look at utilization of a specific thermodynamic equation called the Nernst equation. The Nernst equation lets us calculate the cell potential under non-standard conditions. All right. And just as a reminder, standard conditions include all gases at 1 atmosphere of pressure, 25 degrees Celsius, and any solutions must be 1 molar. So if your cell setup is different from this standard condition set, then you can't just use the reduction and oxidation potentials and say, well, this is the potential of my cell. You have to utilize the Nernst equation to correct for those non-standard conditions. All right, so what does that look like in terms of a formula? Well, that non-standard cell potential is going to be equal to the standard cell potential minus R times the temperature over N times Faraday's constant. All right, remember N is going to be the number of moles of electrons that are being transferred by that redox reaction. And then that is multiplied by the natural log of our reaction quotient. And that reaction quotient is where we are going to be able to correct for non-standard gas concentrations, right? Sorry, gas partial pressures or non-standard solution concentrations. All right, so we can use this formula to determine where the redox reaction is in terms of direction. All right, in other words, towards products or moving towards reactants. All right, remember that Q value compared to KEQ tells you which direction things are moving. All right, so what do we do with that? All right, if our standard cell potential is positive, then we want Q to be less than 1. In other words, we want to be still moving towards equilibrium, right? We want that Q value to have more reactants than products. If our E cell is negative, then we want Q to be greater than 1 so that we're on the product side, all right? So more products than reactants. And in general, what you can do is if you have a cell potential that is negative, all right, a standard cell potential, I should say, all right, you can manipulate the temperature and you can manipulate the concentrations of things to see if you can make that last portion of the Nernst equation positive enough so that you can overcome that negative standard potential. So it is a way to make a cell that would normally not run. All right. By the same token, it is a way to make a cell that would run not run. All right. So by utilizing the changes in concentration, we can impact the cell potential under non-standard conditions and move it either more effectively running or less effectively running. It depends on what your goal is. All right, so let's look at what these problems looks like. So we have an electrochemical cell. It's set up under standard conditions with cobalt and iron ions forming cobalt ions and iron solid. We've got the reduction potentials of those two half reactions. All right, first up, what is the cell potential and will it run? All right, so we know that the standard cell potential is going to be equal to the oxidation potential plus the reduction potential. All right. Well, right now we have two reduction potentials. One of these is an oxidation. So we have to look at our reaction. So we've got cobalt to cobalt ions. So cobalt goes from an oxidation number of 0 to +2. So it has been oxidized and it has lost 2 electrons. Iron goes from +2 to an oxidation number of 0. So it has been reduced and it has gained 2 electrons. All right. So that means that the reduction potential for cobalt needs to be rewritten as an oxidation potential, means it's positive 0.28 volts versus negative. So we're not going to use this one. All right. So we come back over to our formula. So we've got our positive 0.28 volts plus negative 0.44 volts, and we're going to have an overall standard cell potential of negative 0.18 volts. All right, this is unfavorable. All right, so the cell will not run as written. All right. So that negative cell potential tells me that this redox reaction will not happen without some extra help. All right. So, well, what if we adjust the cell concentration? So what if we instead have 0.5 molar cobalt ions and 1.5 molar iron? Will the cell run then? All right. So the first thing we need to do for this is find Q. All right, so for this particular reaction, it's all balanced in terms of charge and elements. We're going to have the concentration of cobalt ions. Whoops, that +2 needs to be inside. There we go. Over the concentration of iron ions, because remember, solids and pure liquids do not go into your Q calculation. So that's going to be 0.500 divided by 1.50. So we're going to get a Q value of 0.33. So that is the reaction quotient. All right. So clearly we have more reactants than products. All right. So now we need to find the potential under non-standard conditions. And this is our Nernst equation. So we need the standard, and then we'll subtract R times T, N times F, and then the natural log of our Q value. All right, so negative 0.18 volts minus. Now, this is a lot. So 8.314. I'm going to keep my units out just because it's a mess. We're going to assume that we're still at standard temperature because it doesn't say we're not. So 298 Kelvin all over. We transferred 2 electrons as part of that redox reaction, and then Faraday's constant. All right. And then the natural log of 0.33. Okay. So we plug all that into our calculator, making sure that we are following our orders of operations, and we should find that we have negative 0.18 volts minus negative 0.014 volts. All right. And if we do that math, we're going to end up with negative 0.166 volts. All right. So our cell potential became a little less negative. So it became a little more favorable, but still unfavorable. All right. Still not going to run. All right. So then what concentration ratio would be needed to make this cell run? All right, so to figure that out, we need a cell potential that at minimum equals 0. All right, we need it to become positive, but at the very least, we got to get to 0. All right, so that means we're going to use our Nernst equation again. All right, but this time we'll put in a 0 for the cell potential. So negative 0.18 volts for the standard cell potential, 8.314 times 298K. Oops, over 2 moles of electrons, and then 96485 coulombs per mole. And then we'll have our unknown natural log of Q. All right. So we end up with 0.18 volts if we slide that to the other side. And then when we do our RT and F piece, we get negative 0.0128 times the natural log of Q. All right, we're going to move that 0.128 to the other side. So the natural log of Q is going to be equal to a negative 14.1. And we take the inverse natural log. We get a Q value here of 7.81 times 10 to the negative seventh. All right, that is small. All right, but what that tells me, we need lots and lots of reactants compared to products. So we need very little of our cobalt ion in our beaker, and we need a whole bunch of the iron ion in the other beaker. And that's going to provide enough pressure, relatively speaking, to push that reaction past that unfavorable cell potential under standard conditions. So you need lots of reactants for this to go. All right. All right, let's look at this next problem. Consider a galvanic cell with the following reaction: two gold ions plus 3 lead solid forms 3 lead ions plus 2 gold solid. Calculate the potential of the cell at 25 degrees Celsius if the concentrations of the lead ions and the gold ions are 0.25 molar and 0.015 molar respectively, and it gives us the reduction potentials for both of those. All right, so we're trying to figure out the potential of the cell under non-standard conditions. All right, so let's think about our formula. All right, we're going to need a couple pieces of information. We're going to need to find the standard cell potential. We're going to need to figure out what N is, the number of electrons being transferred, and we're going to need to calculate Q. All right, so all of that needs to get done. I'm going to do that off to the side. All right, let's start first with our cell potential. How about that? So our standard cell potential is going to be equal to the oxidation plus the cell potential of the reduction. All right, so if we look, we go from +3 to oxidation number of 0 for gold. All right, so it gained electrons. There's your reduction. All right, and it did so 2 times that. So it gained 6 electrons. All right, then lead went from 0 to +2. So it lost electrons and was oxidized, but I have 3 leads and 3 lead ions, so it lost 6 electrons. So N is going to be equal to 6. All right. That means when we look at our reduction potentials that were given in the problem, we need to take lead's reduction potential and make it an oxidation. So plus 0.13 volts plus 1.50 volts. So we're going to have an overall standard cell potential of 1.63 volts. All right, so we're going to need that. All right, next up, Q. All right, Q is going to be the concentration of lead ions cubed divided by the concentration of gold ions squared. All right, so for gold, we have 0.250 cubed over 0.0150 squared. All right, so we plug that into our calculator and we get a Q value here of 69.4. So lots of products are present in these beakers. All right, so now we have everything we need. We go back over to our formula. We plug in our standard cell potential. All right, 8.314 for R. We're at 25 degrees Celsius, so 298 Kelvin. We said we're transferring 6 moles of electrons, and then we've got 96485 for Faraday's constant. And then we'll need to take the natural log of 69.4. All right, so we're going to get 1.63 volts and then minus 0.0181 volts. That is this whole piece computed out. All right, so we're going to end up with 1.62 volts. All right, so that setup, that concentration actually took away from our cell potential a little bit. All right, so that's not great, right? We want our cell to produce as much as possible, to do as much work as possible. So by adjusting our concentrations of ions in the way that this problem has set up, it has actually removed some of that potential to do work. All right. All right, let's look at this last problem. All right, the overall reaction for a voltaic cell is cobalt 2 plus nickel solid forms cobalt solid plus nickel 2. The cell potential is positive 0.16 volts when the concentration of cobalt ions in the cathode is 1.5 molar, calculate the concentration of nickel in the other anode for this case. So if we want to get to the concentration of nickel, then that means I'm going to have to find Q, right? That's going to be my unknown first. And then from there, I can figure out the concentration of nickel. All right. So I know that the cell potential under non-standard conditions is equal to the cell potential under standard conditions minus R times T divided by N times F times the natural log of Q. All right, so again, I'm going to need the standard cell potential, and I'm going to need N, and I'm going to need the non-standard cell potential. All right, well, the non-standard cell potential was given at 0.16. All right, so let's start with our cell potential. All right, now I see that we do not have these given this time, so let me just write them up here for you. All right, we're going to have cobalt going to cobalt solid, all right? And that is gaining 2 electrons. So here's your reduction, and it gained 2 electrons. Then we're going to have nickel going to nickel plus 2. So that lost 2 electrons, it was oxidized. All right, so N is going to be 2. All right. If I look up the reduction potentials, all right, I'm going to find that my standard cell potential is equal to negative 0.28 volts plus 0.26 volts, which equals negative 0.02 volts. Well, that's very interesting that that is negative. All right, if it is negative, then it cannot be a voltaic cell. This is an electrolytic cell, but we're just going to go with it. All right, if it's voltaic, that means it is favorable in the direction as written. All right, so it is producing electrical current. All right, if it's electrolytic, it is the opposite. It is unfavorable as written, and it requires electric current to run. But we're just going to go with it just for, yeah, because we're already here. So we have 0.16 volts for our non-standard cell potential, negative 0.02 volts for our standard cell potential. We've got 8.314 times, temperature's not given, I'm going to go with 25 degrees, divided by 2 moles of electrons being transferred, and Faraday's constant, 96485. And then our natural log of Q as our unknown. Okay, so we're going to move that 0.02 over, and we'll get 0.18 volts on this side. All right, and when we do the mathematics for this middle piece, the RT over NF, we get negative 0.0128. And that's going to be times the natural log of Q. All right, so then the natural log of Q is going to be equal to negative 14.02, which means that Q is going to be equal to 8.15 times 10 to the negative 7. All right, so that's our ratio of products to reactants. And we know that Q is equal to the products, which is nickel plus 2 ions, divided by the reactants, which is cobalt plus 2 ions. They don't have any coefficients, so I don't need any powers. All right. And of these two numbers, I actually know one of them. All right. I do not know what nickel is. That's our unknown. But I do know that cobalt is 1.50 molar. And that's going to be equal to 1.5 times 10 to the negative 7. So if I multiply both sides by that 1.5, I'm going to see that the concentration of nickel that I need in my beaker is going to be equal to 1.22 times 10 to the negative 6th molar. All right, so what that means is I need lots of reactants, very little product. I need the system to push by having pressure with that excess reactant. I need it to move towards that product side by having that buildup of reactant. Okay, I apologize for this problem being a little hinky. All right, I don't love that that cell potential was negative under standard conditions, but that is the way the problem was written, so that's what we had to work with. All right, so I hope that you now appreciate how handy the Nernst equation can be. All right. Most of the time, when we run these cells, whether they're electrolytic or voltaic, they are not run under standard conditions. We don't have one atmosphere of everything. We don't have one molar of all the solutions. And we don't necessarily have a temperature of 25 degrees Celsius. So it's good to have a way to calculate what that cell potential is in reality under non standard conditions. And that gives you an idea of how well your cell will run as built versus as predicted, if you want to think of it that way. All right. Let me know if you have any questions.